In this video, we're going to finish with some of the remaining proofs about cyclic groups. So this stuff is more bonus content. Alright, for some of the bonus content, we claimed earlier that the definition of order of a group is also the size of the cyclic subgroup generated by G. And in fact, the observation is that the powers of G up to the order is the cyclic subgroup. Well, here's the proof. We know the definition of cyclic subgroup is the powers of G. Using the division algorithm, you can write K equals Qn plus R. So G to the K is equal to G to the R, as we've observed before. And so you can actually rewrite it as E times G, G squared up to G to the N minus 1. And so that's the forward direction. If the size of G has order n, then the cyclic subgroup also has size n. That's not using this fact yet, but it's one we might have to use. Although, right, because I just end up doing it directly. Now on the reverse direction, suppose your cyclic group has size n. Then if you look at the sequence E, G, G squared, so on up to G to the N, this has N plus 1 elements. And so not all N plus 1 elements can be distinct. There must be a repeat. That's called the pigeonhole principle. In other words, there exists an I less than J with G to the I equal to G to the J. In other words, there's some two elements in this list that are the same. Well then, by properties of groups, I can multiply by G to the negative I on both sides. Cancel, get the identity, use properties of exponents, and have G to the J minus I on the right. And now I have E equals G to the J minus I, which means that the order of G is J minus I. By this previous argument right here, that implies that the size of the cyclic group generated by G is J minus I. If we're assuming that the size of that cyclic group is N, oh wait, let me be more careful. The fact that E is equal to G to the J minus I actually tells you that the order of G is at most J minus I. And this strict inequality allows us to make sure that this J minus I is not 0. So we're definitely in the case that we're dealing with a positive integer. Good. All right then. So G is at most J minus I. This implies that the size of the cyclic group generated by G is at most J minus I. But since we are assuming that the size was N, and the largest J minus I could be was also N, we have that J minus I is equal to N. So actually I is equal to 0 and J is equal to N. The repeat you have must be the first element and the last element, which means that G to the N is equal to E, and that none of these other elements are equal to E. So the smallest positive power says that G to the power is equal to E is N, which is the definition of order. So this is a bit of a bonus video. This is a proof that subgroups generated by a subset exist in complete generality. The first part is that if you've got a set I, and for each little element in here you define a subgroup of G, H sub I, then the intersection of all these subgroups is also a subgroup. This is often a homework problem in a graduate algebra course. And so it's worth pointing out this set, by definition, is the set of things that are in every subset. I say that because normally in set theory, in the proof writing course, we only talk about intersection of two sets. This is an intersection of arbitrarily many sets, but it's still the same definition. a universal quantifier saying that something belongs to every one of these subsets. So how does this proof work? Well, for x and y in this large intersection, we need to prove that the product is in this intersection. Well, what can we do? For any I in the index set, you have little x and little y are in that subgroup h times I. Well, then x times y inverse is also in h sub I. That's one of the versions of the subgroup criterion. Well, then since it's in h sub I for every I, then by this definition of universal quantifiers, it must be in the whole intersection. And so you're closed under multiplication and inversion, you must be a subgroup. So why do subgroups generated by a subset exist in general? Well, you define them to be this crazy intersection. It's the intersection over all subgroups of G with the property that S is a subset of H. So I should be careful here that sometimes we use this notation for subgroup. And so by this previous claim, this set here is in fact a subgroup. And by this fact here, it does contain the subset S. This intersection is also non-trivial because the set G is one of the factors in this intersection. So there is actually something on the right-hand side to intersect. And since every single last one of these subgroups contains the subset S, the subset S is in this intersection. And so this intersection is non-empty, and it contains the subset S. Moreover, this is actually the smallest subgroup containing the subset S. Why? Because if you let H be any subgroup containing the subset S, H appears as one of these factors. And this intersection is a subset of that H. And so there you go. Subgroups generated by a subset always exist. I think I mentioned before that this construction in general was pretty crazy. And it is. Subgroups generated by two elements can be very large. Even if the order of x and y are both 2. You can actually get the order of this group to be 2 times n for any integer n. Or you can get it to be infinity. There are examples like that too. So, these groups in general can be very, very, very strange, which is why we only focus on cyclic subgroups for this class when we're talking about generated by an element.